Yes. Uh, well, first of all, I would like to say thank you for your availability and then your contribution, yeah, to share your knowledge to my students. I'm sure, I'm sure all my students, they will have a new knowledge which is very useful for them. I'm sure. And then hopefully also they can share it to other people in the future, yeah, so that the knowledge will be shared uh, among us, and then they also get the benefit. Okay.
I hope so.
Yes. My students, hello. Can you please turn your camera on so that our honorable keynote speaker can also see you, can also see how is the Indonesian students look like.
Hello, everyone. I'm happy to see you. I hope that this lecture would be helpful for you and your future. And thank you from Dr. Alini that invited me for this
No problem. No
lecture.
problem. Yeah. Okay. Can we start? Like, oh, first of all,
Yes,
I would like to introduce you to all my students first. Yeah.
sure.
So
Yeah.
yeah. So students, this is our honorable keynote speaker today, and then his complete name is Dr. Mohammad Mahdi Abaei. I just call him Mahdi because we are colleagues before. We are colleagues in University of Exeter before, so we, we we are just a very good friends at that time, and then still the relationship, a good friendship is we still have carry on until today. And then today we are very have a good opportunity to have a very good lecture from Dr. Abaei. He will present the reliability, which is very he is very good at it, and then he is very expert in reliability. And then now he works in TU Delft. TU Delft is some university in the Netherlands, and also before he is carry on his postdoctoral research program, he finished his PhD in Australia. I can't remember what is the university. Marty, can you tell?
Tasmania, University of Tasmania.
Yeah, so he finished his PhD study there in Tasmania, and then he got his PhD degree there. And then after that, he continued with a postdoctoral research fellow in University of Exeter, and then where I was meeting with him at that time, yeah, in the University of Exeter, and then now he works in TU Delft. Okay, I think without further ado, Mati, please you can start your presentation.
Sure.
Okay, and then. Yeah.
I will share my screen just in a minute.
Okay, thank you.
Could you see all my screen?
Yes, we can see it.
Okay, perfect. Yeah, once more, thank you very much for inviting me as a guest lecturer. I hope that this lecture would be very helpful for you. The topic that I would like to discuss further is a fundamental discussion regarding the reliability engineering from the concept and the way that we can use in real engineering problems. Just in a minute. I will give you a few learning materials which will be very helpful for you if any of the students is interested in their future career to have a self-study. This material is very helpful, and they can go further in detail by themselves step by step. During the course, if any of the students have any question, they can easily raise their hand and ask, then we can try to answer anything come up. I also sent all this material to Dr. Arini, and after the session, Dr. Arini can share all this material to you. And also, there is no need to write down anything from this PowerPoint. I also shared this PowerPoint with Dr. Arini, and she can send it to you after the lecture. This book is very important and in somehow it is a Bible reliability book, so you can read through it. I send the PDF to Dr. Aini, and also you can purchase this one from the bookstore, An Introduction to Reliability and Maintainability Engineering. Because of my interest in Bayesian inference, which is one of the good approach in reliability engineering for prediction, there are a few books in this concept, like Bayesian Inference for Probabilistic Risk Assessment. It is a practitioner guidebook with lots of examples and coding examples that help you how you can implement reliability problems. This paper, Bayesian Inference in Probabilistic Risk Assessment, is a concise discussion about this book, which is the same author. This paper is very, very concise, in about 20 pages, but it has many good ideas about how the reliability is. It is a quite advanced topic. So before you understand this one, it is very good if you read this An Introduction to Reliability and Maintainability Engineering book. Besides this one, there are lots of research institutes around the world that you can go to their research group and see what they are doing, read their publications, and improve your knowledge in reliability engineering. I would like to share some of this group, which is very helpful for you. Professor Faisal Khan group in Memorial, they have a Center for Risk and Reliability Assessment with many different range of studies, specifically in reliability engineering in Memorial University in Canada. And this is the link that you can use later. Professor Peter Fangelder from the Technical University of Delft. His group is also very strong in reliability engineering, from concept to probabilistic modeling, risk assessment, and they have many projects and also good publication in the field, which you can easily read through them and improve your knowledge in reliability engineering. And also Professor Daniel Straub group in Technical University of Munich, which they have a very strong research group in reliability engineering. These three one is one of the best research group in the world regarding the reliability engineering, but there are many other research group as well, which you can easily find them. The learning objective of this lecture would be 3 steps. One, I would like to share some knowledge that can be helpful for you to understand the basic concept in reliability engineering that help you. What does it mean exactly? What does it mean when we say reliability engineering, and how we can define a problem by reliability engineering? Learning about different types of uncertainty, how we can define uncertainty that help us to model the reliability of a system or a structure. And more importantly, find your track to developing your knowledge for advanced reliability assessment. Based on these materials, books, papers, and roadmap that I will share with you to find it as a simple way for self-study in your future career. So the main concept in reliability engineering coming with the uncertainty. So the most important thing is that what is the uncertainty and how we can define uncertainty in any kind of engineering problem, from marine engineering, civil engineering, natural hazards, everything. So Basically, there are two types of uncertainty that we always see around us, even in nature or in system or in the structures. The first one is epistemic. Epistemic uncertainty is a kind of uncertainty that inherently happens, and we cannot do anything with that. It always happens. We cannot reduce it, we cannot increase it. This uncertainty is always happen. If I want to give you an example, it is like dropping a coin. If we drop a coin, for example, one time, and we want to see that if it comes down head or tail, all of you will say that this uncertainty will be 0.5, because if we drop a coin and we want to see that if it is head, it has 50% chance. If we drop this coin 10 times, this is the same. If we drop this coin 1 year, it is the same, because if we want to observe tail or head for this coin, it will be 50%. So it means that this uncertainty is epistemic, which means that we cannot do anything with that. It always happens. And with a certain amount, like the dropping a coin, 50%, for example. What would be in the nature? So in the nature, it would be like the sea wave. We cannot do anything with the sea wave. It always happens in the nature. Sometimes it is 1 meter, sometimes 2 meters, sometimes 3 meters. What we can do is that we try to predict this uncertainty to see that how much time for example, we observe sea wave of 8 meter, 3 meter, for example, 5 meter. And then if we understand that, for example, sea wave height is for observing a sea wave height of 8 meter is 50%, so it means that it is very high. It means that we should do something with our structure in marine environment. If we want to observe these sea wave heights, so we should do something. Other example like this one, this sea wave will come to offshore wind structures or ship structures. So we need to know how much is this uncertainty to come interact with our structures. So what we can do is only predict an amount of observing a specific wave height, for example, in the nature. But we all know that these sea waves will always happen. We cannot reduce these uncertainties. For example, we cannot say that we are doing something to reduce the observing sea wave height of 8 meter for example, North Sea, because it will happen. In somehow it comes from God nature. It's not from human-based nature. The other one example is like earthquake. We cannot do anything with the uncertainty of observing earthquake. It will happen. Or volcano as a nature eruption of the mountain. It will happen. We cannot do anything with that. But it has some uncertainty. For example, one time in each 500 years, but it will happen. The other one is earthquake for damaging the bridge. All these one are epistemic uncertainty, which mostly are caused from limited data or knowledge, because we don't know how, for example, how God create the waves exactly. It is somehow caused from limited data, limited knowledge. We don't know anything about the volcano. We don't know anything about the sea waves, observing the sea waves. Other uncertainty is what we can do something with that. It is related to a statistical uncertainty and what we are trying to model the nature. We know that we cannot do anything with the waves, but we can model the sea wave. We can do something with wave mechanics. We can do something with earthquake modeling. These kind of physics, modeling the physics of the nature, related to alloteric uncertainty. This will result to uncertainty regarding the model of the physics. For example, in the fluid mechanics, the Navier-Stokes model that we are trying to use for evaluating the fluid around the structures, it will be a model of the process, and it will have some uncertainty, which we can do it with that, because if, for example, we assume that a fluid is a potential fluid, so we disregard the viscosity in the fluid, it will increase some uncertainty. These are somehow what we can say about alloteric. The other example is like the performance analysis of these structures, like offshore wind turbine. The model that we use to evaluating the response of these structures with considering these mooring systems needs that we use some dynamic equation based on Newton laws. This will result some uncertainty because our mathematics, our physics are not completely represent exactly what in the nature will happen. So it has some uncertainty that we can reduce, or if we couldn't use a good model of process, the uncertainty will increase. If we wouldn't use some good assumption regarding the mooring dynamics, the uncertainty will increase. If we use some good assumption, good physics, good mathematics regarding to modeling the mooring line, then the uncertainty will reduce, and our problem will be close to the real nature. Like these example, for example, in the for dynamic analysis of these structures, if we use some assumption regarding the structures, some assumption regarding the mooring systems, some assumption about the fluids, to model the whole structures in the nature, it all is about alloteric. So alloteric uncertainty is all about physics, all about mathematics that we are trying to use to model the structures, the nature, anything. Like the wind tunnel. When we use, for example, structures, airplane, ships, anything in the wind tunnel, so this is somehow representing the real situation of the wind structures in the nature. But again, it has some uncertainty because it is not really the full scale. It is something closing to the real case. So it has some uncertainty that based on our assumption, based on our facility, we can reduce this uncertainty. Is there any question regarding the uncertainty? You can go further if you want.
Dr. Abaei?
Yeah, sure.
I think question and answer, it's better to put it in the end of the presentation. So after you present, it will be better like that. Okay, thank you.
Sure. No worries. So how we can define reliability? We understand what is the uncertainty, so we want to know that how we can define reliability. General reliability formula is defined as a probability that a system or a structure will function over some time period t. So it is all about the probability and functionality, a probability of observing that this function would be reliability, and this is the probability. This is a probability density function and this is the cumulative probability density function. So all is about probability over the time. All reliability function have a function like this one. So at the first time, the reliability is 1. It means that the structure is almost in the best condition. Like, for example, when you buy a pump. So the pump in the first yearly of its working, we know that in the in theory, not in reality, in theory, we know that in the time 0, the reliability would be 100%. So we show that it will be working 100%. So by increasing the time, this reliability will be decreased until it fails. Sometimes some structure, some machinery will fail, for example, after 2 days. Some structure or machinery will fail after 200 days. It depends on the systems and your problem, and this function will be changed. So the derivative of this function over the time will be resulted to this function. This is probability density function, which represents this one, and this is reliability of your structures. So there is another definition in reliability engineering which link to reliability formula, and it is bathtub hazard rate curve or failure rate curve. Failure rate give an instantaneous rate of failure in time. For example, it will give you that, for example, you have a pump, okay? You have a pump and you want to know that when it will be failed. Failure rate will give you some instantaneous rate in this sense, that in previous pump that this company had, these companies observed 10 times of failure over 5 years. So the failure rate will be 10 divided by 5 years. So we can say that the failure rate of this pump is 10 times over 5 years. This concept is very important that we can help us to define this reliability. So the failure rate always have some function like this one. In the yearly of the functioning of the specific machineries or structures, there is a burning period which is very highly failure rate, because there would be some unexpected failure which come from the design. For example, you observe that, for example, in reality, you observe that for example, you buy a pump, and when you start the pump, you see that after 2 hours it breaks down. It is all about the designing, which most of the machineries have this imperfect design, so you observe that this system breaks down. But after this one, so it doesn't mean the useful life. If this burning period finished, you will have some useful lifetime, and this failure rate is very important for most of engineering problem to define that how long these structures will be, or this system will be react in its operation time. Like the example I told you about the pump that has, for example, 10 times of failure over 5 years. And why the remaining useful lifetime structures finished, then these structures or the machinery will drastically increase its failure rate to break down. You can see that, for example, around you, there are lots of buildings that have more than, for example, 15 years or 100 years. And you can have it make sense that, oh, this structure will be failed soon because it is in the wear out period. And it is very harmful. And the reliability engineer or the mechanical engineer, civil engineer, they should do something to reduce this wear out. And while they predict this useful lifetime, they can predict that when the structure will go to this period, and then they do something to increase the safety of operation. There are some mathematical representation of these that can link failure rate to reliability engineering, which all about the derivative of this function over the time. For more information regarding these concepts, I will give you some hint that you can read through the book that I shared in the first slide. And now I will give some question that you can think further in later. You can while you read over those books, you can answer this one. It is not difficult actually. So based on what we have discussed here regarding the reliability function, I mean this function, and probability density function, like this function. There are some concept, very basic concept in a statistical or probability model, which the material that I sent to you, and they will give you this insight that what is probability density function and everything. So while you read those material, you can answer that. What is the cumulative distribution function? And how we can define from cumulative distribution function the reliability. And then you can answer that if the cumulative distribution function is like the one minus reliability function or not. How we can derive reliability function from failure rate, and how can we predict mean time to failure of a component from reliability function. What does it mean by mean time to failure? For example, we have these reliability function or this failure rate. We want to know that what is the expected time of the failure. For example, the structure will fail from this time, this time, this time, this time. What is the most expected? The most expected is the average or the mean or the expected time that you can observe from this area or this one, which will be the centric area under this curve. For example, it will be something like here. It will be something like here. And from here, it would be something like, for example, here. It means that it is the expected. So you will learn about this one while you read chapter 1 to chapter 4 from the reference 1 that I gave to you. Just let me, I go back easily to chapter 1 to chapter 2 from reference 1 from this book. While you read these chapters from 1 to 4 from this book, you can easily understand these concepts. So After understanding the uncertainty and the reliability function, now we want to say that what are the key parameters in reliability engineering. We know that reliability has two types of uncertainty. One is aleatoric, one is uncertainty. We know that reliability related to time. We know that reliability has some concern regarding the functionality of a structure or system. So based on this understanding, we can say that the key parameters in reliability is probability, that define that how much is our structure in Hertz condition, or how much is possible that our structure will fail from the reliability function. Time, which is very important for us to know that when this structure will fail, or how long this structure will perform safely. The other criteria is the performance of the system or structure, how this structure will behave in an operation. So, how system, component, a structure will fail. It means that how we should define the dynamic of a system. So it will be aleatoric uncertainty. Since we need to model the process, we need to model the physics, or we need to do some experiment if we want to understand the performance of a system. If we want to know how a system will behave. So this is aleatoric uncertainty. The operational condition. This is another factor in reliability. What is our environment condition? Like wave load, seismic, humanity, vibration, anything. It is epistemic uncertainty. So anything regarding the operational condition, which we need to know when we want to model the performance of the system. So I believe that now you should understand that when we want to model a reliability of a structure or a system, we need to connect operational condition to the performance. Operational condition is something that comes from environment, and the performance of the structure is something that comes from the physics experiment. When we connect these two together, it means that aleatoric and epistemic uncertainty all together will play important role in reliability engineering, which help us to define the expected time of failure and the probability that we observe this kind of failure. Now let's think and try to understand these four parameters in some real problem. Just I would like to let you think in 1 or 2 minutes by yourself, and then I will discuss. Just in your mind, think that define the aleatoric and epistemic uncertainty in these examples. How we can model it. What is defined by performance here? For example, for these structures, how we can model it? What is operational condition here? How we can model it? This is very important that we try to digest these key parameters. Just think for 2 minutes or 1 minute. I will then discuss further. I just want to let you have a free mind and a little bit thinking about what we discussed in previous slides. Don't worry about the questions. Just freely think about this problem. Okay, so if we want to make a differentiate between alliterative and epistemological uncertainty in this example, we need to understand what is the environment and what is the physics that link us to performance and link us to operational condition. So here, the performance will be related to dynamics of these structures, like dynamics of the floating object, the moving system. Here, how we can model the moving systems based on some physics of assumption, like this one. It could be based on, for example, finite element method. It could be the hydrodynamics could be based on CFD or potential theory, like boundary element method, like this one. So it is the physics of these structures, modeling the aerodynamics of the blades, and all is about the physics of modeling these structures. So it is alliterative uncertainty. What all come from the environment, from these operational conditions, like wind, wave, current, all is operational condition, and it is epistemic. It will always happen. We cannot do anything with that, and it has some certain amount of uncertainty. So for any kind of problem, we need to do the same thing. It doesn't have any difference between ocean, airplane, dynamics, anything is the same. So here I would like to say very short a story about the structural reliability engineering. It is quite the same, but it has some point that you can use for a structural reliability engineering. We have some concern regarding, for example, reliability of a system like pump. Sometimes we need to know the reliability of a structure, like offshore wind turbine, anything, building like this one. Performance of a structures is a link between resistance of a structures, what it experienced environmental load. So it means that, for example, if we have a structures, the wave come to the structures, it encounter to the structures, how much this structure will resist this environment load, how much it can resist. So it is a playing between load and resist. Again, it is a playing between operational condition and performance. This is simply defined by limited state function or failure function, which is defined by resistance minus load. The load is what comes from environment like wind, ocean, this one. Resistance is what the structures can resist. For example, in these structures, the load is wind, wave, current. It comes to a structure. These structures should resist these loads. So the resistance here is something like, for example, the mooring line. We can define which part is our concern. For example, in this example, we want to have a concern on mooring system. We don't want to see any fracture or rupture in our mooring system, okay? So the resistance should be the mooring. We wouldn't like this mooring fail until, for example, observing a tension of 400 Newton. Okay, if that makes sense. So resistance is again related to physics. For example, here modeling the mooring system, the loads is related to environment. So if it is this function, if this function is more than 0, it is safe. It is lower than 0, it is fail. So let's make a very simple example for mooring failure. Let's have an assumption that we want designing a mooring system, a mooring line that resists 200 kilonewton. So resistance is equal to 200 kilonewton. The wave, however, the wave load is random. It could be very high, it could be very low. It depends on the nature. Sometimes the wave come to 8 meters, sometimes come to 5 meters. It's very, very stochastic. So we need to define the stochastic response of the mooring. While we use this stochastic modeling based on the available commercial softwares that come from physics model like CFD or potential theory. So let's assume that we do this physics of model. And we observe that based on these stochastic wave heights that come to the structures, we observe that the mooring tension is about 4 different values: 150, 100, 110, 240. What we need to do is that we try to check the resistance of the mooring. We design this mooring. We have some material that we are sure that this mooring will resist this amount of tension. But while the wave load comes to the structures, and based on our physics of model, we understand that, or based on our experiment, we observe that the mooring system will observe different kind of value, like this one. In some part, the value is positive. In some part, the value is negative. So among 4 of these experiments, we observe that 3 of times it is positive and 1 time it is negative. So the probability of failure is easily 1 divided by 4. So it means that for this example, there is 25% chance for observing failure in mooring system. For this example, the mooring system will fail 20% of time. This is how the structural reliability works. For those who are interested in the structural reliability, they can use these 3 materials. Lecture note from Professor Sorensen from Aalborg University. PhD thesis by Fritz Hansen. It is very good thesis regarding structural reliability engineering. And the works by Daniel Straub. Just remember these notation A, B, C, because in the slides I give you some reference, like reference 1, 2, 3, which is regarding the first slide I showed you, and A, B, C are the reference regarding these, structural reliability references. I shared all these material with Dr. Abaei, and she can share it with you. And depend on what you are interested, you can read through them and learn about both of them in details. And don't rely on these references. These are just give you some interest, some insight you can do further. Because, for example, the Professor Sorensen, in his lecture notes, he gives some basics of structural reliability based on first order and second order reliability engineering. However, Fritz Hansen has modern reliability aspect based on Bayesian network. And Daniel Straub, again, he used some kind of a structural reliability based on what Sorensen is done and what Fritz Hansen done. It's altogether. But there are many other resources in the world. There are different type of approaches for reliability assessment, like SNEA, which is qualitative approach. Some companies in oil and gas, for example, companies, nuclear engineering companies, they use this qualitative approach. It is all about discussion. For example, they write down in a logbook that how this process will fail and how we can prevent this failure. It is all is qualitative. Fault tree analysis, it is quantitative approach, but it is based on constant failure rate. It is this, which is not very good for complex problems like the one we have in structural engineering, like the failure in mooring system, or even in complex operation like machineries. However, the fault tree analysis still has some popularity among the researchers because it will give some good insight. Still, it gives some good insight regarding the failure propagation over a system or operation. There are many good new approaches like Bayesian network, machine learning, like Bayesian inference. For Bayesian inference, you can use reference 2, 3, and B. Markov process, you can use reference 1, chapter 6. For those who are interested in more details in structural reliability, they can use this UQ lab from ETH University. They use, yes. Is there any question? Okay. UQ lab web page developed by ETH. It is very good, but very advanced one. And deep learning, which I didn't provide any references in this lecture, but for those who are on neural network, deep learning, this approach is also very, very powerful for structural reliability. So there are many approaches that we can use for reliability assessment. I want to give you very short review over the Bayesian approach, and that help you to understand how it works. And then if you are interested, you can study further by your own. Bayes theorem is based on a simple probability theorem that comes from posterior, likelihood, and prior. This formula is a concept of probability model, while it comes to probabilistic analysis, it comes with very powerful in terms of predicting parameters like mooring failure, like structure failure based on our data. How this, what is the mathematics behind this one? I want to give you the insight that go to the references that I shared with you regarding the Bayesian in the last chapter, and then you will understand what is this formula will say. But here I want to give you the main concept that helps you. So in any kind of problem, we have data, some sort of data that come from physics of model, from experiment. We need to use this data and model the process to see that how the parameters related to the functionality of a system, like mooring one, then behave. This will help us to predict the failure of this particular parameter. The model of the process defined as a likelihood. What represent about the data is defined as a prior, and the final function is a posterior. So the prior is a probability of a parameter that represent what we can guess, what we can imagine from our data, from the available data that we have, the current situation of the data. The likelihood is a probability that represents the behavior of the structures based on the model of the process, like failure of a component based on Poisson distribution as an assumption. You can read reference 3 and also reference 2. This will be very helpful. So at the end, the posterior represent what is thought given both from prior information and data just as seen. There are this sort of definition is mostly used in the literature for Bayesian theorem. But the main concern is that how we can define this prior, how we can define this likelihood. What does it mean exactly in real problem? So this definition is not really helpful for us. When you go further in the real problem, it will give you some good insight that what will be this definition is based on the references that I provided to you. Sometimes in the literature they use data evidence refer to likelihood, but these are just using the word in the literature. Don't worry about these concepts. I mean, these wordings. Use these references that I told you, and also some online courses that I will share with you later. You can understand the basic concept of Bayesian in very, very good way. If I want to show you that what does it mean? So in any problem, we have some prior knowledge. For example, we have some prior knowledge that this mooring system or this pump will fail like this probability. For example, 50% has a chance to fail in time, for example, 10. While we model the structures, while we model the system, we see that no, it wouldn't fail like this one. It will fail like this one. Then we multiply this to this, we will get this probability. It is what we expected from the failure. So in Bayesian theorem, the prior will help you to give some guess. Prior will give you some guess. This guess will be used later for evaluating your likelihood. The likelihood is what you define based on model of the process, based on the physics. And these together will give you some function like this one. For example, while your prior is far away from, it is your guess. While your guess is far away from your likelihood or data, which we say that what we evidence, then the posterior will shift to the data. Just give you another interpretation. Prior is a very raw data. For example, you don't know anything about your structures, like the mooring system. You can just guess that, okay, I think this mooring system will fail 2 times each year. It is just based on a guess, no more than that. we can say that, okay, we agree with you. This can be failed 2 times every year. But we ask an engineer, we ask him, okay, just try to model the physics of these structures based on CFD to see that how this structure will react, how this moving system will react. Then, based on these observation that we get from the physics, we say that no, this structure, for example, the mooring system will fail 2 times, more than 2 times. It is not correct. The guess we had is not correct. So we need to use data and prior to see that what is the final expectation of our mooring system. So observation will play an important role and model of the process to get the precise failure probability. These data is something related to alliterative uncertainty that we can reduce based on physics of the model. This is the main concept behind the Bayesian, but based on those references and these online courses, you will understand more in depth. Here I want to give you very short example based on one of the work that Dr. Abaei and I had done in University of Exeter regarding the same concept. So let's see, this is the structure for tidal energy converter. So we want to know that when the mooring system will fail, we want to know that what is the failure rate of this mooring system. Having said that, this system is not yet operate in environment. It is just in the early design. So we don't know any, we don't have any actually operational observation like the current structures that are operating in sea. It is just a concept. So based on Bayesian theorem, we can say that we want to know that what is the probability of system failure for our problem mooring failure based on the data that we have. So we need to model the epistemic and alliterative uncertainty. Epistemic is what is related to environment, okay? But this environment give us some system failure. The environment come to the, structures lead to failure of the mooring system. We want to know that. And the alliterative is the way that we need to model the physics of the system. The physics of the system, for example, can use based on the CFD or modeling the structures for mooring behavior. For constructing these alliterative uncertainty after the physics of the simulation for the model of the process, we need to define a function. This function is a Poisson distribution. Poisson distribution is somehow a kind of function that can help you to predict that how much you will observe system failure, mooring failure, or how much a time you will observe earthquake will happen. You can later back to slide 4 and think that how this function can work and what does it represent in terms of failure rate and reliability function that we discussed later in slide 4. and why it is useful here for predicting mooring failure, and how it can be linked to physics. The prior limited knowledge that we have, it means for this particular example, we don't know that how much is the mooring failure rate, because it is not yet installed in the environment. So there is no information. What we can do is that we use some kind of non-informative prior, uniform prior. It means that we assume that all mooring will fail with the same amount of failure rate. What does it mean? It is something like that, but we can, it is an assumption, like a guess, like a prior. We say that, okay, we don't know anything. We can say that the mooring failure rate is like 400 times over 2,000 of operation time. It could be incorrect, it could be correct. How we can understand based on the model of the process, and so based on this, the failure rate is unknown. What we have done is giving a very naive assumption, which is not true, which is just a non-informative prior. And the data, which is very important here, come from experiment, come from simulation, come from the physics that can help us to use in the function. These experiments are derived from, for this particular example, for example, Dr. Arini developed the physics of model based on Orcaflex for modeling the mooring line. Then what we do with these physics, we use these data to interpret the differentiation of the mooring tension as an observation, how these mooring lines will be behave based on the safe limits. We wouldn't like this mooring system that we want to design fail, and we know that the resistance of this mooring system would be 200 kilonewton. You can see. So all these dots that we observe from observation, from the simulation, all these dots, it means that will lead to failure of our mooring systems. But these data are, those ones are in the safe zone. These are not in the safe zone. And this is how this distribution is worked. So based on these, we need to predict the failure rate. These data will help us to predict the true value of these failure rates. And there are, in more detail, it is discussed in our work. But I want to say that, do you think if it is the only solution for solving this problem or not? The answer is that actually it is not the only solution. There are many other ways that we can model this uncertainty. We can use different kind of model of the process and different kind of simulation experiment. These two is very important for prediction. I want to give you a very quick review for helping you to read more and improve the knowledge in Bayesian inference. So there are 3 different very useful courses in Coursera. Coursera is a platform which is very good for learning new course material. Not only in Bayesian inference, for any kind of subject like control mechanics, I don't know, in data analysis, fluid mechanics, anything. There are lots of good material. Here are some examples for Bayesian. There is a course named Bayesian Statistics from Concept to Data Analysis. This is the link. You can use it. Bayesian Statistics, Techniques, and Model. There are lots of good examples, and the lecturer give you very good fundamental and advanced courses based on the Bayesian statistics. Here, there is a mixture model Bayesian statistics. It is very more advanced one. So for those who are interested, they can start with this course and then learn this course. And then if they were interested, they can go further for this course. There are many good softwares like GenAI. It is free for academic use. And you can download it from this one. It is just simply for Bayesian network, not for Bayesian inference. There are some differences, but you can download this software. Winbox, OpenBox, and JAX, S10. This for software for advanced Bayesian inference, which you can learn about it from reference 2 and 3, and also listening to these 2 online courses will help you how you can use these softwares. Read reference 2 and 3, and also this paper will give you some insight that how this prior will play important role in Bayesian inference. Thank you very much for listening to this lecture and also inviting me. If there is any question, I'm happy to try to answer if I can do that.
Thank you, Mahdi. This is very useful and also helpful material for my students. Okay,
Thank
are
you.
you happy? Yeah, are you happy with question and answer session?
Yeah, sure.
Okay. Now, students, please, if you have any questions about the content, about the materials, for reliability, and what he just explained, you can ask to him. And then please mention your name first, because Mahdi doesn't know your name yet. He's still new for you, and also you are still new for him. So please mention your name and then just straight what your question is. Okay. Want to take first? Okay, who is this? Someone raised their hand. I can't see it. Okay, Fakih. Okay, please, Fakih.
Okay, thank you. Firstly, I'm going to say thank you for such an amazing explanation and reliability engineering. Actually, in my thesis, I work in reliability analysis. I conduct reliability analysis using based on historical data file layer. It very depends on the distribution of the data. As I know that to analyze the reliability, there are parametric and non-parametric approach. So the question is, which one is better to analyze the reliability, and what is the advantage and the advantage of the parametric and non-parametric approach? Thank you.
Thank you very much for your question. I want to say that it is very important question that you say, and it means that you have some good insight in reliability. It is very important. I want to emphasize that it is very important question that you ask. Actually, it depends on the problem. sometimes, for example, we want to say that we have a part of data and we want to use parametric distribution like the Weibull. But in the nature, these parameters cannot exactly follow up the Weibull distribution. So for this case, definitely we should go further for non-parametric. So for non-parametric problem, we must use a non-parametric solution while we are quite sure that there will be no distribution that can represent the behavior of our data. For example, for the failure of a pump, while we know that based on the historical data, most of the failure of a pump will represent like the exponential distribution. So for this particular, there is no need to go further for non-parametric solution. But while, for example, we come through to failure of ships, vessel transiting restricted water, and we want to know that if this vessel will touch the seabed or not. These times that want to touch the seabed, it come very complex behavior. Okay, so for this problem, it is definitely good that we go for non-parametric solution. And for non-parametric solution, there are many approaches like Bayesian, deep learning, corrugate modeling, these sort of things. I hope that this answer could be helpful for you.
It's very clear. Thank you.
Thank you.
Okay, thank you, Mahdi. This is such a very good question and answer, and then you also explained it very well. I'm sure Fakih understand, and then it will improve his final project so that he will get A. Yeah, Fakih.
I mean.
Okay. Any other questions? Okay. While waiting for my students' questions. Other questions. I have questions, Mahdi, because
sure.
When we work together at that time, you just do the reliability and I do the structural analysis. So it is very separate. Yeah, it's a very separate topics. Yeah, and focus. And at that time, I was wondering, but I didn't have time to ask you. Now I have time to ask you, so that's why I give the questions to you. Okay, you just mentioned, you just mentioned that we have what we call, we have resistance and also we have load. Yeah, resistance means design. Something about designs. Failure about design, and then the load is about nature behavior. And we know that not all the design work in nature. For example, because here we study about power plant. Power plant is not dealing with nature. Power plant is something that we create. The environment is something that we create. Like, for example, we work with steam power plant. So we burn the water so that the water becomes steam, become vapor. So we're not dealing with wind or current or wave. So it's not about nature. It's about something that we create, the environment. Now, how we do the reliability analysis if we are not working with the nature itself? That's the first question. But second question I will ask you later. No, I think one by one, because it will make my students confused if I give you more than one question. Okay.
Yeah, sure. That's a very good point. So for the power plant, you are correct. We don't know anything. We are not dealing with like wind or wave, but we are dealing with operational condition. The operational condition in power plant would be like vibration. It could be like temperature, like pressure. These are the uncertainty in our operation that we must consider them in the our problem. In that case, we need to know that how this operational condition will change. For example, in the power plant, if we know that if the pressure in the vessel increase from, for example, some certain amount, there will be some blowout. So we need to monitor the pressure. Monitoring the key factor is very important in reliability. In power plant, like natural gas, for example, we had a project in natural gas distribution. In natural gas distribution, it is like something like the power plant. For that one, the concern of the project was that they control the pressure of the vessel in some certain amount. If this amount come up, then the operation will damage. If it is in a certain amount, it will be phased. So in that case, the operational condition is playing the key role, like vibration, operation, something like that. It is in somehow representing the thing that we had in sea environment, like waves or these things.
Okay, thank you. One more question.
Sure.
Still at the same topic. Yeah. So here in the power plant case, it means we have to consider about the operational conditions. Okay. Say that we have two kinds of failure here. Yeah. Just say, for example, that the most extreme load is the most extreme things which cause failure is vibration and pressure, for example. Yeah. Now, should we combine those two failures, vibrations and pressure, when we analyze reliability, or we need to separate it? So I mean, in its things which cause the failure, should we combine it or should we just separate it when we analyze reliability?
This is one of the, concern in reliability actually. While we have a different kind of failure, so it is necessary that we consider them together or not. So you put the concern in a writing actually. It depends on the operation. So based on the operation and the data that we have, we need to do some analysis to see that if these two failures have some correlation together or not. If these failures have some correlation together, definitely we should use them in a one package, not separate. Because, for example, we can imagine that increasing pressure in a vessel can lead to increasing vibration in the vessel as well. So while there are some link together, it means that we need to consider them together. But still we can define the probability or reliability of a system with considering separating these two kinds of failure, and we can get some result which is still in somehow correct, but for more precise reliability, it is better to integrate them together in one system, which in context we can say that system of systems or accumulative failures. We need to consider all of them together. It would be much better.
Thank you very much for the answers. Students, now I get back to you. Is there any question? More questions to ask? I think reliability is a very good topic because it is needed by all designs. Yeah. Is that correct? Because if we design something, that means although it is not manufactured yet, though we need to predict. Yeah, we need to predict which is possible for us to know when our design is failed and then when it is survived. So I think this is very, very useful. Yeah.
Yeah, exactly. Not only for design, but also for monitoring the operation as well. It will be very important for health monitoring of the structure. Yeah, you are right.
Okay, any other questions? Fadil, your final project is also reliability, right?
All right, ma'am.
I think some students here, yeah, in my class, they took reliability topics as their final project. So not just Fakih, yeah. So I think some students, other students, they also take reliability as their final projects. I don't know.
Okay.
Maybe those students want to ask questions because this is very good opportunity. We have a reliability expert, yeah, who talk directly to you, who give explanation, information. So I think you should take it. Don't take it for granted, yeah, because he is here now. Okay, and then reliability is new concept in our study. Yeah. Well, maybe it's not new for you, but we are not really focusing on reliability in our study. So I think this is very good opportunity. So maybe you have some questions. Oh, okay. While waiting, okay. So I have some. I have other question, Mahdi. So
Sure.
do you think all designs should be analyzed, its reliability concept, or we can skip it? I mean, when we can skip the reliability analysis.
Sorry, Dr.
How important reliability analysis? Yes.
Sorry, I miss your voice. Sorry, could you repeat it again?
Yeah. Okay. So how important reliability analysis to a new design? I mean, when we have to evaluate the reliability, and then when we can skip the reliability when we design something.
Actually, when we want to, the main concern of all industry is all about the money. So while we come to the money, it means that we must reduce the operational cost, we must reduce the maintenance cost, and increase the safety. So in that case, reliability engineering becomes very important in the design, that we try to optimize the design of the structures, both in the cost of manufacturing, from the cost of operational maintenance, to reduce the maintenance cost and also increase the safety of the operation, increase this, the safety of the crew in that particular industry.
Okay, I got it. I got it.
Thank you.
Okay, before I close the session, I give you last opportunity to ask to Dr. Abaei if you have still some questions to ask about the reliability evaluation. Everything is clear?
Excuse me, ma'am. Excuse me, ma'am.
Yes.
Can I ask one more time?
Yeah.
Sure.
Yeah. Sure.
Okay, thank you. As I read on the first reference that you suggest, the book by Charles Abaei, I found that the reliability improvement depends on the failure rate. For example, for the constant failure rate, preventive maintenance doesn't impact to the reliability. And in contrast, for the component which has increasing failure rates, the preventive maintenance is very powerful to increase the reliability. Please explain me how to imagine that in the real life. Thank you.
Thank you for your question. This is again very good question that you asked. Actually, when we want to go for predictive maintenance, so it means that we need to consider the reality of the operation. The constant failure rate is a naive assumption which cannot help you to use increasing hazard rate. Like just let me I share my screen again. It is very important question that you asked. Just let me. Could you see my screen?
Yes, yes.
Okay. So the constant failure rate is something like here, but in the nature, this assumption is not really, good in reality. For time-dependent failure rate, which is something like this one, we need to use a specific and true representation of the process for the model. If we want to use, for example, a parametric solution, as you said, for the parametric solution of these part, one solution is that we use a Weibull distribution. Because in the Weibull distribution, we use a power law. The power law use non-constant failure rate. And also we can use other approach like Bayesian inference or deep learning, anything like that one, that use different kind of data in time and considering the correlation of this data over the time. While we use the correlation of the data over the time, it means that we reject the constant failure rate. And for the predictive maintenance, time-dependent reliability is very important. But I can say that again, it doesn't mean that the constant failure rate is not useful. Because in most of the case in our problem, like the design of machinery or power plant, when we observe previous data, we can see that, okay, all this machinery behave like a constant failure rate. So in that case, there is no need that we use time-dependent failure rate, because we just making complex our problem. However, the problem is not complex. It is exactly representing the constant failure rate. One of the powerful approach that use constant failure rate, and still it is very good, is Markov chain. Markov chain, the fundamental concept of the Markov chain, which discussed in chapter 6 is in Abaei. You can read through that one. The whole story is based on constant failure rate. However, it considers different kind of system together, like system of system. Like you have two pumps, you have a gearbox, you have a shaft. All of them are working together, and you want to know that how this whole system will fail. For this one, you can make the assumption that all these components have a constant failure rate, and then use a complex model in terms of modeling the different type of failure for those whole system, okay, and see that how it will be failed with constant failure rate. So again, I can say that it very dependent on the problem that you want to use. Both constant failure rate and time-dependent failure rate is very, very important. And most of the time, the time-dependent failure rate will lead to use non-parametric solution, for example, or some solution that need you to use, for example, parametric solution such as Weibull, such as Gumbel, such as, for example, if you want to predict the long-term failure of a mooring system with parametric solution, you can use Gumbel distribution. With Gumbel distribution, you can predict the long-term prediction, which is not constant failure rate. And again, it is a parametric. So there are very dependent on your problem. Is that was clear?
Yes, very clear. Thank you. Can I give another question?
Yeah, sure. Feel free.
Is there any kind of software to analyze reliability that you suggest?
Yes, there are lots of good software in reliability engineering. Just let me. Okay. If you are interested in structural reliability, UQ Lab is open source software based on MATLAB. It's designed by ETH. You can easily download it. It is a very advanced one in reliability engineering, and also for coding based on Bayesian inference. These softwares is good: Winbugs, OpenBugs, JAGS, and STAN. Each of them has very good, lecture tutorial. There are lots of good tutorial, and these two courses will give you some good insight for using JAGS, which is very similar to OpenBugs and Winbugs. But you can read through that one in STAN as well. And also, you just read through these two references, which help you how you use Winbugs or OpenBugs for using in your reliability engineering concept. And also these two courses. Just okay, sorry, my yeah, it was a hang. So yeah, these are the softwares that you can use, and they're all very good tutorial in the website. But what I provided here is also very good material that you can learn more for advanced probabilistic modeling, like Markov chain Monte Carlo based on Bayesian inference, by using Winbugs or OpenBugs, JAGS, and UQ Lab from ETH. UQ Lab from ETH is very good for structural reliability engineering, but you can use those methods in power plant system engineering as well. And in UQ Lab, it has many good examples and approaches, which are specifically good for non-parametric studies. Since you told me about, it seems that you are very interested in reliability engineering. So just let me, this course, mixture model, you can see that, okay, it is very advanced one. It is better you read, you listen to these two courses as well after that. This course is mixture model based on Gaussian process. Gaussian process is a kind of non-parametric solution. And you can then learn about this one as well and use it in your example as well, in your studies as well.
Okay, thank you. Thank you very much for all the explanations. Okay, last opportunity. I will raise the last opportunity to all of you. Or if you're not sure how to say it, or if you're not confident with English, I can interpret it to you. So I think it should be okay, Mahdi, if they want to ask in Indonesian,
yeah.
but I will.
Sure.
Yeah. For other class than class 4, class 1, class 2, class 3, you are also welcome to ask questions here. I know that you study, maybe your knowledge or even the subjects is not reaching the reliability, but it's okay if you are interested in then, and then if you're not sure how to say it, I can interpret it, help to interpret your questions to Mahdi. Okay, everyone is clear?
I want to ask.
Who is this? Okay, any question? I hear someone saying something?
My name is Alvin Pangbarok. I want to ask a question. As you have stated before, there are not only one way to determine the reliability factor. So, is there any some kind of conditions or something to apply this one of these methods, or you use any kind of methods you like, and maybe how much different the results might be within each results. No, each methods to determine the reliability factor. Thank you.
Thank you very much for your question. If I want to give you something that makes sense, for example, in fluid mechanics, there are lots of approaches based on Navier-Stokes, for example, CFD. Sometimes people use finite difference method. Sometimes people use finite element method. Sometimes people use potential theory. All of them have some good accuracy, and all of them will give you some good results. But it highly dependent on the problem. For example, if you want to use some big structures in the sea environment, so you can easily use potential theory. Even though that if you use CFD, again, you will give some good results. The same is true in reliability engineering. So if you use, for example, Bayesian inference, you will give some good accuracy in your problem. While if you want to use, for example, deep learning, again, you will have receive some good results. It depends on how you create your methodology, your framework. Your framework is more important than the tools that you want to use. Sometimes people use, for example, very complex model for Bayesian inference, for example, but they have not good accuracy because the framework that they want to link the problem for failure modeling is not good. Or sometimes people use very complex problems, complex methods to solve the problem, but it doesn't necessarily. You can easily use fault tree and to get the result. For example, for failure of a pump, it is very easy that you use fault tree because it is something that it becomes clear based on the lots of good operational data that we have for design of the pump. But for recently designed structures like offshore wind or offshore structures or other problem in your case in power plant, some things that are very new when we have not much useful data or something that we need to have more accuracy in terms of predicting its performance. So we need to use some robust framework based on the predictive tools. So it depends on the problem, and all of them have good answer, good result. Depend on your solution, depend on your framework.
Thank you. I think the answer is clear enough here to answer.
Thank you.
Yes.
Yeah. Yes. Very clear enough. Thank you, sir.
Thank you.
Okay. I think I don't want to disturb your time. I know that you have to go to work. You have to go to work, and then you have many things to do, yeah, because this is also working day. This is not weekend, so I don't want to disturb. Again, I say thank you very much for your availability, and then also your willingness to share your knowledge. This is very, very useful for my students so that they can understand reliability further, and then they can also apply it to their final project, or maybe in the future they need it. We never know, but I'm sure that this is very useful. Thank you again, Mahdi, and
Thank
then
you.
also happy fasting for you. Hopefully our fasting,
You too as well. Thank you.
hopefully our fasting will be accepted. Okay, and then last time, please give applause. Turn your microphone on first. Turn your microphone. Okay, and then 1, 2, 3. Let's give applause to Mahdi. Okay. Thank you. Maybe we can see again later, yeah, in the future, and then maybe who knows, we can also you can visit Indonesia and then visit us. Thank you.
Yes, thank you. Thank you very much for inviting me, and wish you all best good. Thank you. Thank you.
Thank
Have a
you.
good day. Bye. Bye.
Bye.